today, we are going to introduce a couple of IoT project for pitching relevant with manufacturing, especially applying the IoT for the legacy manufacturing systems. So myself have been involved with two pitching projects. One is a project I would summarize that the project is more towards to data collection, and the other project is more towards to after you collect the manufacturing data, how to you apply the advanced machine learning technology to process that data, to analyze that data. So this is the first one. This one is we work with Sheffield, the local manufacturer, and they trying to deploy the IoT technology and industrialize the IoT technology to the shop floor. So we have heard about a lot of IoT technology, and the IoT technology can be generally applied to many sectors. For example, home automation, for example, smart cities. And now we are more focused on how to apply the IoT technology for the manufacturers and how to industrialize the IoT, and that they can help manufacturing business. And there are quite a lot of a challenge to industrialize IoT for manufacturing. The first is, as you see the picture, so this is a typical manufacturing environment, not the most advanced, but is an average level of manufacturing facilities. They can have a lot of hazard. For example, the weight, the oil, and the high temperature, dust, and they supply with industrial power supply, which is very high voltage, so can be 300 watts. And normally there would be very poor network infrastructure. For example, here there is no Wi-Fi. So can this IoT smart device fit in that harsh environment? This is first challenge. The second challenge is on the shop floor, they have many data points, and they have different type of data, for example, pressure, for example, the temperature, current, and they need different type of device. And all the data will come to a place. We wish they can run a very smooth flow into our database and store in the right and safe way. That is a large scale deployment actually. And actually to manage 1,000 device, a fleet of device on the shop floor is very difficult. And we are also very interested to invest how to deal with that problem. And the third is not like other industry that maybe the IoT is the first thing arrive and they can draft a totally new architecture for the information system. Manufacturing industries have their own information system. Actually, it's developed much earlier than the true IT industry. So they developed the first generation of the information system that developed for the controlling of the machine, and that is reference to operation technology. And modern operation technology include the industrial control system, which is include the PLC, this kind of controller, and they have also involved with manufacturing information system, which involved with SCADA, MES, if you have heard about it. This is a more low level of enterprise system. If you know the top level maybe is enterprise system is ERP, for example, SAP software. And the fourth challenge is whether we can continue to develop and deploy the IoT application to the shop floor. Because IoT is quite a new technology and it's still developing, it's evolved very fast. And we need to integrate with a lot of systems, and we need to upgrade it frequently. Can we continue to develop and deliver them to the shop floor? So to face with the challenge, we have tried multiple experiments to test the device, IoT device and IoT sensor to figure out whether they can fit into manufacturing environment. So we have a test through multiple generation, as you can see. For the left side, that is we're using Raspberry Pi, we use Arduino, that is kind of educational IoT device and sensors. You can see they have a temperature and humidity sensors and ultrasonic sensors. They are quite cheap. It can work. We have put it in the shop floor, but it will soon lost the connection. They can't survive in that harsh environment. And the second generation, we have improve the layout of the package, make it more small, so we can put in more convenient space in the shop on the shop floor, and with better connection method, you can say. And the third generation, where other upgrade about the case, and we put the one industrialized IoT gateway, and both the industrialized and the general IoT device to test which one can survive better, if with a proper protection. And we are also testing the industrial sensors, as you can see here. And the fourth generation, we remove out the educational IoT device. We just keep the industrialized IoT device on the shop floor and let it run for a long term to collect the data. And you can see this is how it's deployed on the shop floor, and you can see the environment around is not an ideal environment for the normal device. And we're also trying to get more precise industrial sensor, and we involve with the more advanced technology like industrialized LoRa sensor. So this is our journey for IoT to industrialized IoT. And this is just a picture show you on the shop floor, we have collected a lot of data points, different, for example, they have flow, they have pressure, they have temperature in different location. And you can see this is just the general environment on the shop floor. So we have talked about the hardware, and let's also talk something about the software. So this is a designed IoT architecture. As you can see on the shop floor, it exists a lot of legacy device which cannot output the digital signal directly. So we need the sensors, and we need some edge device to capture that signal and convert to right format of data. And they also have some smart device. Maybe they can direct collect the data and convert to right format for communication. Also, they have an industrial control system. For example, the PLC box. They also can output some digitalized format of information, and it's sent through the MQTT, most popular protocol for IoT message. And then we try two pathways. One is send the data and store it on local server. For example, we use InfluxDB and Postgres database. And that for the whole data, we can monitor condition, and we can send the alerting in time. And it can also send to the cloud, which we cooperate with Siemens. We can send the data to Siemens Mitesfield. And on the cloud, they can acquire more powerful computing resource. So it can have more analytic work happen on the cloud. And the analysis result also can report on the dashboard, a remote dashboard. If you open a browser, web browser, you can see the data. And it can also, we have also purchased a very big display on the shop floor, so the operator also can see the state of the production line. So this is a short demo that we, before we try the real data, we create some simulate case. That is a simulate device, simulate data, and simulate network. This all happened in Siemens Mitesfield. And this is one application I have created for demo purpose. So this is interface of Mitesfield. And this is a pump. They have a current and pressure in, pressure out. And you can see the current state and the history state. So then we are looking at a problem that, so if we develop the IoT applications and we want to test it on the shop floor, and we are aware that we need a lot of round of tests, both in the developed environment and production environment, and how to keep the continue to upgrading and debugging the application, but avoid the stop of production. And then we find this CI/CD workflow and container technology is quite helpful. So the basic workflow is you develop your application remotely at your home, and you build, you just combine everything into a executable application. Either is a Docker container or something else, and you test this solution with the virtual environment and with the device, physical device, and you deploy them. And if something wrong or you figure out something you need to improve, then you can redo this loop. And the benefit of this is you can see here there is a rolling update technique. So they have launched multiple servers at the same time, and to update, it will have a rolling update. It means they shut down some of the servers at one time, but keep at least one service running. So the switch off of the different version of software actually will introduce no downtime for the actual service. So the IoT application would not, the end customer, for example, the data collection process will have no downtime during your update or debugging your software. And they have some other interesting technology called load balancer and self-healing. They can distribute the computing load to multiple devices and to keep them optimal utilize and reduce the downtime for the whole system. So this is the dashboard we create. So you can see they have a real-time figure for which we collect for shop floor and history data. And we also monitor our device, include the IoT device and the sensors, so we can figure out when it's not working. Currently, we are also trying to connect the IoT system with the industrial control system. So for example, we want to know the tension and speed of the conveyor chain. So we have tried different solutions to connect the industrial controller. We communicate with the industrial communication protocol, and we use IoT gateway or smart POC to connect them and send out the message through the IoT communication protocol, which is MQTT, to our target network and to our IoT server. We are developing some just open source Python package to make it convenient to connect to the industrial controller by a IoT way. So that is some main content for this project. Welcome any question. Thanks for listening.
Thank you, Boyang. That's great. I know that there's a question from Jonathan from Green Custard who asks, why is fleet management of industrial IoT devices a challenge for you?
Because first, the fleet of the IoT device on the shop floor is not a single type of device. They have many kind of device, many kind of IoT device, many kind of sensor, and they have function of each device made different. So you probably can update all of them in one shot, and how to maintain them, how to update them gradually actually is quite challenging things. And maybe let's sit back, how to keep all of them stay online. is also a challenge at this moment.
Thank you. Alexandra has a question for you. Alexandra, do you want to ask Boyan?
I'm sorry I'm late, but yes, thank you very much, Boyang. I was just, I came here at the tail end of your presentation, and so this monitoring for conveyor belts. So what was the purpose there? Is it just simply condition monitoring?
So conveyor is they will carry the part of the time, and the chain always break down, and the industry partner maybe not quite understand why it break down. And we know this chain is driven by motor, and the motor, the control of the motor will differentiate the tension of the chain and the speed of the chain. And we want to, and we know there are degradation procedure for this chain as the time went by, but we can't quite understand the nature how the chain break down. So we want to collect the data, and then the data can be used for more advanced data analytic, for example, the machine learning and predictive maintenance. Then we can understand the nature how this quality decrease, and we can predict the time when it would break, and the possibility of it when the quality issue will happen.
Thank you.
Anandarup has a question as well. Do you want to ask it, Anandarup, or shall I read it? He asks what, go on, Anandarup.
That was a great presentation. My question is, like at the plant floor, since you need dense deployments for monitoring all those parameters, so do you like simultaneously transmit all the data to a gateway, or do you use a mesh kind of architecture?
So the last sentence, would you like to repeat?
Like all the data from the end devices, are they simultaneously transmitting to a gateway and then maybe forwarded to a cloud, or being processed locally, or the end devices talk amongst themselves and form a mesh configuration?
Okay, so the connection is not straightforward because they are located, of the device are located in different region of the factory, and the infrastructure of the factory is quite isolated. So they need to go to different gateway. So actually it's also a challenge how to collect the data and device for different region of the inside of one big factory. So they have a lot of work to collect the data for different space for the factory, different pace of factory. It's not like that synchronized.
Okay, thank you.
Yeah.
Boyang, there's one more question from Herman. He asks, what's the monetary cost associated to the non-educational gateways? Is it hundreds or is it thousands of pounds? And how many more times more expensive than a Raspberry Pi? Okay, so here I give some just cost related figures. So Raspberry Pi is about £30 to £100, depends on the configuration you are buying. The actual cost is not totally associated with the Raspberry Pi itself, also associated with the sensor. For example, this type of distance sensor is just £5, but this type, if you can see my mouse, so the industrialized, the LoRa sensor would cost about £200. So the cost is also associated with the edge device and the sensor together. And it also depends on the how many data point you need to collect, how many sensor you need to deploy. And so it's really depends on the size of your project, and you demand how precise and your environment, how harsh is environment, and you need a better protection plan. Thanks. Hope that answered the question. That's great. Thank you.
Boyan, can I ask a follow-up question on that?
Sure.
So obviously you are positing the difference in cost between the small 5-pound sensor and the LoRa 200-pound industrial sensor. Does the same apply for the edge gateway device? So whereas you are currently using the 30 to 100-pound Raspberry Pi, presumably for industrial application later, there will be a specialized embedded computer board?
Mhm. So, so if you may understand the question, so is that a question? So how much computer power you need for the?
No. I mean, is there also in essentially, would they be using an industrial version of the Raspberry Pi in the final deployment, akin to, you know, the industrial LoRa ultrasonic sensor compared to the 5-pound component for testing?
Okay, so if I understand, the question is why you are using expensive industrial device rather than a cheap version of a low-cost device.
No,
So
that's not the question. The question is, presumably, is there a difference in you're using Raspberry Pi or Arduino for the moment just for the testing purpose? Will they have to develop a specialized computer board later on if they actually install it in the factory, or will they actually be buying Raspberry Pis? Is that the idea, and put them as a
okay.
gateway for data collection?
So for when we develop the application, for example, we write the script in Python, we would first use the Raspberry environment to test, and then we will the next round we will test in the industrial gateway. The one reason why we prefer the industrial device is Raspberry Pi is very open sourced, and the security of the the update of the operation system and the application inside of Raspberry Pi is not that robust, not as robust as the industrialized version. And maybe the other reason we use the expensive LoRa ultrasonic sensor is we need to place it into a very harsh environment. And that is where a lot of the moisture and high temperature and high voltage, and it's very hard to deploy the communication method. For example, Raspberry Pi need they have Wi-Fi, they have Bluetooth, they have Ethernet, but all of these are not working in that environment. So we have to use LoRa, and only LoRa can or send the data out of a metal box. Currently, we can't have a final recombination list, but we are trying different industrial environment and see whether which one can better fit into that industrial environment.
Thank you.
Thank you. Boyang, would you like to move on to the next presentation? I think that's with the one, project with Cambridge and Alexandra and Zhang. Thank you.
Thanks.